I will let you introduce yourself.
All right. Good morning, everyone. My name is John Donohue. I'm from the Institute for Quantum Computing. Thank you for having me for the Phys 10 seminar today. I'm excited to talk a bit about quantum and pop culture. So there's going to be some tech throughout this. So if any of the clips, for whatever reason, you can't hear them, you should be able to hear them through your computer. If you can't, please unmute yourself and yell at me. If there's any questions at all, don't worry about raising your hand. Just unmute yourself and yell at me if you want. So some of you are first-year students. So just to give you kind of the lay of the land, I'm the scientific outreach manager at the Institute for Quantum Computing. We're a research center located as part of the university. We have 2 buildings on campus: the Quantum Nano Center, which is right in the center of campus, on the edge of the ring road, and the Research Advancement Center, which is just north of Columbia, kind of in the in one of the fields up there. So the Institute for Quantum Computing isn't an apartment in the same way that physics is an apartment. Instead, it's a multidisciplinary research institute. We have faculty members from physics, chemistry, electrical engineering, computer science, and 3 different faculties in mathematics, 3 different departments in mathematics, all working on problems related to quantum science and quantum information research. So that's 32 different research groups, about 190 graduate students, as well as a whole bunch of undergraduate researchers working on co-op terms and doing part-time research. So if you're interested in that, take a peek at our website, follow us on social. I put the links here. We post a lot of stuff about what kind of quantum stuff is going on, pictures from inside the fabrication facility, that kind of thing. And if you're interested about IQC stuff, by all means, ask me questions about it as well. So what are we studying at IQC? We're studying this effectively. We are studying the quantum realm. It doesn't look a lot like it does in this picture from Ant-Man. A lot of times it's used in these contexts to just mean something complicated, some magic dust there where all the rules are broken. I don't really like that interpretation of quantum mechanics being a place where all the rules are broken, because quantum mechanics does have a very strict rule book. We know the rules of quantum mechanics. Quantum mechanics is a theory that describes the world below what our eyes can see. And, through things like Schrdingers Equation, we have found the rules of quantum mechanics. And so far, every experimental test we have for those rules has shown that quantum mechanics is a perfect description in many ways of what's going on below the surface. There are certain things where we don't know, there are certain things that we don't quite know, for example, how quantum mechanics interacts with gravity. But this is partially because we're very incapable with our current technology of designing experiments that would show a discrepancy. But in terms of the experiments that we can do, quantum mechanics describes them very, very well. So what are the rules of this sub-microscopic universe? Well, we have a rule book. We have our rule book of quantum mechanics, just like we have our rule book of classical mechanics. The difference is that some of these rules don't quite match up with what we think about in the classical world. For example, in the quantum world, energy is quantized, not continuous. If I think about a light dimmer switch, I can go from anywhere from all the way on to all the way off and anywhere in between. But if I think about photons, I either have 0 photons, 1 photon, 2 photons. I never have half a photon or pi photons. There are still definitely rules that things have to obey in the quantum realm. We must obey the superposition principle. It must obey the Schrödinger equation, but it doesn't strictly obey the rules that we kind of see in the world around us. For example, if we take a very narrow view of what locality means, the fact that what I do over here can't influence what happens over here, then quantum mechanics doesn't seem to obey that. Or things like determinism. If I roll a dice and don't look at it, well, it doesn't matter. It still came up with a value. If I roll the 3, even if I don't look at the 3, there's a 3 down there. But quantum mechanics doesn't necessarily obey the same rule of determinism, where things that I don't observe don't necessarily have an exact or knowable outcome. When we talk about quantum mechanics, especially when we talk about things like quantum institutes, and we'll be talking about some of the newfangled quantum computing stuff, it's easy to get the impression that quantum mechanics is something new that scientists are just starting to figure out. The first thing I want to say is no, that's not the case. Quantum mechanics at this point is old.
You've muted yourself for some reason.
Don't know how I did that. Okay, hopefully I wasn't muted for too long.
Only for a couple seconds.
Okay, perfect. So quantum mechanics is not new. It's old hat. So quantum mechanics was kind of figured out in the first half of the 20th century. probably most famously by these faces at the Solvay conference in 1927. And since the 1950s and 60s, it's already given us a lot of technologies that we use in our everyday life. Things like light emitting diodes, things like MRI machines, things like lasers, things like semiconductor circuits. These are all technologies that are based on quantum mechanics that we would not have if we did not already understand how to use and how to utilize quantum mechanics. So quantum science, it's not necessarily new at this point. This is, quantum mechanics is not PS5, quantum mechanics is Atari 2600. So what is new about quantum? And even at this point, kind of 20 years old about quantum, we're taking those tools that we've learned about in quantum mechanics, things like MRI machines, things like lasers, and mixing them in with things that we've learned about information theory in the same timeline, things that we've learned about how to compute things, things we've learned about processors and transistors. And what we're really studying now, what kind of the new quantum is quantum information, studying how we treat the rules of information science when we mix them in with the laws of quantum physics. So this has led to like a whole massive quantum hype train. So for example, in 2009, the Institute for Quantum Computing, we were founded in 2002, but we kind of grew a lot in 2009 with a $50 million investment from the Canadian government. There's been a ton of other like massive multi-million, even billion-dollar investments from governments to kind of push forward quantum information science in the last 10 or so years. In 2017, the European Union invested €1 billion. In 2017, the National Laboratory for Quantum Sciences in China invested $10 billion. The United States government at the National Quantum Initiative invested $1.2 billion 2 years ago. And just earlier this year, the Indian government invested over $1 billion as its quantum technologies and applications message. So billions has been invested in quantum technologies, which is kind of why it kind of gets that, allure of being this new science. We've also seen a lot of big stories coming out from industry. So a lot of major players such as Google, IBM, and Microsoft have all dedicated teams to study quantum computing, trying to build the quantum computer. They all look a little different, but we saw things like, for example, Google's experiment last year, or maybe earlier this year, time has lost all sense of meaning, where they showed a quantum advantage for a certain quantum computational task. We've also seen things like IBM, which has on their website a quantum computer, a small quantum device, more accurately, that you can interact with and code your own quantum circuits with. We also have a whole bunch of startups, like, for example, Xanadu, a photonic quantum computing company located in Toronto, who are also working to build a quantum computer. In parallel to all of this, we see a ton of this happening. So kind of on an exponential increase, we've seen people just use the word quantum to describe anything, even if it has really absolutely nothing to do with quantum mechanics. For example, the Yeezy quantum shoes. I'm sure they're very comfy sneakers. They look pretty sharp. They have nothing to do with quantum mechanics. The quantum bowling ball looks like a nice ball. Nothing to do with quantum mechanics. The quantum sleeper anti-terrorist bed. It looks like it might keep you safe in certain circumstances. It has nothing to do with quantum mechanics. Some of them have the good jokes. For example, UPS Quantum View tells you exactly where your package is, but gives you no damn idea when it's going to show up. And the quantum conditioner releases all the particles from your hair to unlock its true wave nature. And if you're in Toronto and you're hopping by Xanadu to look at their photonic quantum computer, by all means, stop by Quantum Coffee on the way. But none of these really have anything to do with quantum mechanics. This is all just quantum buzzwording. Effectively, what they're trying to do here whenever they apply quantum as a buzzword is kind of the same thing that they would do. It's almost like a deluxe, but like applying the word deluxe, but a bit more tech heavy. So it makes it feel like it's high technology. It makes it feel new and exciting. And this is something that's also used a lot in fiction. So to kind of summarize this, The Onion got way ahead of the ball and in 2009 posted this satirical article, "Sci-fi writer attributes everything to mysterious quantum flux." So a reading of his Eclipse of Infinity reveals that the new science fiction novel makes more than 80 separate references to the quantum flux, a vaguely defined force the author uses to advance the plot, resolve conflict as needed, and account for dozens of glaring inconsistencies. So effectively, whenever something comes up that he needs to write his way out of, the quantum flux comes along. It's the equivalent of pixie dust or magic in the universe. We see this also come up in a lot of very, very popular movies. For example, Ant-Man and the Wasp, which I'll play a quick clip of right now. Oh, lost it. There we go.
It's quantum entanglement between the quantum states of Posner molecules in your brains.
Yeah, that's what I was thinking. Do you guys just put the word quantum in front of everything?
All right, hopefully that audio came through for everyone. If it didn't, if anyone was unable to hear it, just yell at me. But yeah, so it's the same thing in Ant-Man and the Wasp. They're using the quantum flux of Posner molecules in your brains to kind of explain away something that they just need the plot to get to. We're just using quantum mechanics as a shortcut. In this case, we're using it as a shortcut to mean something high tech, but there's another way that people use it as a shortcut. So I'm going to play a montage of about 5 clips. And what I want you to think about is just how exactly they're using quantum mechanics here. What do they want you as a viewer to understand about quantum mechanics? The first clip is pretty quick. Just pay attention to the book that the certain celebrity is reading. All right.
People have a lot of misconceptions about California, but none of them are really true.
None of them.
What's that? Quantum physics?
Yeah. Always been fascinated that light could be a particle and a wave. I was going to study it in college, but then I got interested in biochemistry and then on a whim settled on linguistics with a minor in comparative religion.
Wow. How'd you end up in a place like this?
The last girl quit. The last girl quit. Can you believe it?
The food court is downstairs. The cookie stand is upstairs. It's not like we're talking quantum physics here.
Like, you should have never had a shot. It doesn't make any sense.
No, trust me, I said, like, I've known this the whole time.
I understand quantum physics more than I understand how you ended up with Cece.
Don't you understand that this is the problem?
All this knowledge about everything, quantum physics, applied mathematics, the infinite capacity of a cell's nucleus, they're all exploding inside my brain, all this knowledge.
Well, first I was going to pop this guy hanging from the street light, and then I realized, you know, he's just working out. And how would I feel if somebody come running in the gym, bust me in my ass while I'm on a treadmill? Then I saw this snarling beast guy, and I noticed he had a tissue in his hand. I realized, you know, he's not snarling. He's sneezing. You know, ain't no real threat there. And I saw little Tiffany. I'm thinking, you know, 8-year-old white girl, middle of the ghetto, bunch of monsters, this time of night with quantum physics books. She about to start some there. She's about 8 years old. Those books are way too advanced for her.
Okay, so what exactly, sorry about the little skip in the middle there, but what exactly are all those clips trying to tell us about quantum mechanics? Well, they're trying to tell us that, you know, I forget the character's name from Corner Gas, but that she's too smart to be, it's weird that she's reading this high-level quantum textbook. They're trying to tell us that, you know, doesn't take a quantum mechanic to figure out where the cookie stand is or whether or not it's part of the food court. They're trying to tell us that, you know, quantum mechanics is easier to understand than how Schmidt ended up with Cece. They're trying to tell us that Lucy's mind has expanded to such an intense thing that she's able to understand both the infinite capacity of the nucleus of a cell as well as basic quantum mechanics. And finally, they're telling you that if you are under the age of 15 and able to understand quantum mechanics, the government is going to shoot you. These are the kind of things that, you know, they're using quantum mechanics as shorthand to do. They're basically saying that quantum mechanics equals complicated. That's the shortcut here. It's not anything about quantum physics. They're just saying, you know, quantum mechanics is rocket science. Quantum mechanics is a label for complex things that normal people don't understand. So I've spent my time, you know, 5 years of my life in grad school kind of thinking about quantum mechanics. So why exactly do people have this impression that quantum mechanics equals complicated? So I'm kind of going to boil that down into 3 reasons why I think people think quantum is complicated, why that kind of is the pervasive tone in pop culture. Also, someone was talking about movies for Bad Science Movie Night. If Lucy is not on your list, then it is not a real list of bad science movies. Lucy is top of the pops.
Already added it.
Perfect. So why does quantum equals complicated? Reason number 1 is it is a little abstract. So as mentioned, quantum describes the rules of the sub-microscopic universe. It's not, you know, something that we can think about in our head and have a clear picture. The same way I can think about throwing a tennis ball in the air, I can have a clear picture of, yeah, it's going to come down again. And one of the most abstract things we talk about in quantum mechanics is the quantum state. So we'll often say the quantum state of the electron or the quantum state of the photon. So what do we mean by quantum state? Well, the quantum state describes a property of an object. So a common example in quantum science is an electron orbiting around the nucleus of an atom. So in this example, we're looking at basically a hydrogen atom. It has a one positive charge in the center, one electron orbiting around it, kind of thinking in that old-fashioned orbital model. So right now we would say the electron exists. The electron is our quantum particle. And the state of the electron is that it is in the inner orbital. The state of the electron is that it's in the low energy ground state. So whenever we talk about quantum physics, it's useful for us as physicists to talk about electrons and that kind of stuff. When we try to expand that to other people, we don't want to talk about electrons. So what other things do we talk about as having states?
What's in the box, Schrodinger?
A cat, some poison, and a cesium atom.
The cat, is it alive or dead? Alive or dead?
Answer him, fool.
It's a superposition of both states until you open it and collapse the wave function.
Says you.
There's also a lot of drugs in there.
Okay, so in this case from Futurama, we have a cat in a box. The question of the cat is not whether or not there is a cat in the box. The question is the cat alive or dead? So when Fry opens the box, he discovers, yes, there is a cat in there. And much to his chagrin, the cat is in the state alive. So when we say quantum state, we mean that property. So the state is alive. Reason number, so we're abstracting a bit there already. Reason number two, people often think quantum is complicated is because it involves a lot of math. And if you want to work with quantum on a deep level, yes, you're going to need a lot of linear algebra and calculus. But the kind of basics of quantum mechanics don't need a lot of math. Why people think it involves a lot of math is probably because of how much we've kind of put Schrodinger's equation on a pedestal. Schrodinger's equation is, the thing you have to understand if you want to understand quantum mechanics. Which, don't get me wrong, there's a lot of beautiful stuff happening in Schrodinger's equation. Once you understand it completely, and as you'll see in some of your quantum courses, when you have to go through all the painstaking effort to calculate the hydrogen atom, you can use it to find things like exactly why all these atomic orbitals have these funny looking shapes. But it's kind of a lot to deal with, especially if you're just getting familiar with quantum mechanics. So let's forget about Schrodinger's equation and let's focus on the key lessons that we can derive from Schrodinger's equation. The first key lesson is that there are discrete energy levels. So just as the electron can only exist in these shaped ones, or if we go to our 2D mind picture of the Bohr orbitals, it can only exist in this low energy state or this higher energy state and nowhere in between. These energy levels are quantized. The other lesson we need is that superpositions are allowed. So if you have a little bit of familiar with differential equations, what that basically means is that if we have two possible solutions to Schrodinger's equation, say psi1 and psi2, if they both satisfy Schrodinger's equation, then any superposition of psi1 and psi2, so a constant times psi1 plus a constant times psi2, must also satisfy Schrodinger's equation. The equation is linear, so I can have a superposition of two possible wave functions. So, okay, what does that mean? What does a superposition actually mean? So we're going to go back to the onion one more time, where the Hagar physicists have developed their quantum slacks. So at a press conference Monday, Hagar physicists announced the successful development of quantum slacks, attractive, wrinkle-free pants that paradoxically behave like both formal and casual wear. With this breakthrough, pants enter a whole new dimension, said the head of the Hagar team. Conventional notions about the properties and possibilities of slacks have been completely turned on their head. So what these, pants scientists have figured out is how to create a pair of pants that exists in a quantum superposition. It is a superposition of both comfortable casual wear, like these pair of jeans, and formal, nice wear that you could wear to, a wedding, like these nice black trousers. In a quantum superposition state, it has a component that is both nice, crisp and casual, and nice, crisp and formal. What these Hagar physicists did not account for was that, yes, I can have these pants in a superposition state, but whenever I measure the pants, whenever I ask them a question, are you casual or are you formal, they're going to collapse to one or the other. Whenever I ask those pants the question, I don't get it's both casual and formal. I get one or the other with a completely probabilistic outcome. it's going to be completely random if my pants are formal or casual, which, if I'm at, grandma's 50th anniversary and suddenly I find myself wearing my holy jeans, might not be the best place for me to be. So let's back up a sec. How do we actually think about this in terms of real things? So whenever we talk about superposition, we always have to talk about it in terms of what we call a set of mutually exclusive states. So two states are mutually exclusive if they are distinguishable and impossible to confuse, and if they cannot both occur at the same time. So for example, the light bulb being on or off. If I have a perfect robot who's telling the difference, they can always tell the difference between on versus off. And a light cannot be on and off at the same time. Similarly, a coin can be heads or tails. I can always tell the difference between heads and tails, and those two possibilities cannot occur at the same time. The cat being alive and dead, the light being red or blue, light switch being off and on, the pants being jeans or formal. These are all examples of mutually exclusive states. This is a kind of a classical idea of information because I can encode precisely one bit of information into this system. If the pants are casual, I'm going to say that's a 0. If the pants are formal, that's a 1. The light is off, that's a 0. The light is on, that's a 1. Quantumly, we can think about the exact same kind of thing. So think, for example, an electron spin. Electrons have a property called spin, and it can either be spinning clockwise or counterclockwise. If it's spinning clockwise by a right-hand rule, we call that spin up. Counterclockwise, we call that spin down. Those are two opposite possibilities. They cannot both occur at the same time. So I can label 1, 0 and 1, 1. Another example, if I have a single photon of light, it carries a polarization. It could be horizontal or vertical, and that polarization cannot be both at the same time. So those two options are completely distinguishable. Okay. The difference when I start allowing these quantum bits instead of these classical bits, which we call qubits, we call a quantum bit a qubit, sorry, is that we're allowed these superposition states. So look at this state, for example, plus, which is a superposition of 0 and 1. And the electron spin, it's like it's spinning both up and down at the same time. So since 0 and 1, since spin up and spin down are both solutions of the Schrodinger equation, this is also a solution of the Schrodinger equation. We use this bracket notation. Don't worry about it too much for right now. All it means is this is the state 0 and this is the state 1. So the particle is both 0 and 1 at the same time. But very importantly, when I ask it the question, are you 0 or are you 1, it will be found as 0 or 1 randomly. It's like the universe flips a coin and I ask the question, are you 0 or 1? It's not going to tell me I'm both. It's going to tell me I'm 0 or I'm 1. The same way the pants will tell me I'm casual or I'm formal. So there's a notion of a measurement basis scenario. I ask the question, are you 0 or are you 1? This measurement basis defines which question I ask the qubit. But let's look at another different quantum state. Let's look at our state 0. So that's our spin up state. If I take this state plus and I also introduce a state minus that just has a minus sign in the middle here, I can actually represent the state 0 as a superposition of the superposition states. In this case, spin up is a superposition of being both the plus and minus superposition at the same time. But if I ask the question, are you plus or minus, it's going to tell me plus or minus randomly. It has a 50-50 mixture of plus and minus components. So once again, the universe is going to flip a coin and tell me I'm plus or I'm minus randomly. So the idea of superposition depends on which questions I'm asking. Yeah, and whether or not it's random depends on what state it is. So this is kind of actually the magic sauce of quantum information. If I think about bits and probabilistic mixtures, I have a bit that's either 0 or 1. I could have something where it flips a coin and gives me a 0 or a 1 randomly, but it's at the end of the day there's a coin flip in there. Meanwhile, qubits, so they always classical bits always exist on this line between 0 and 1. Qubits, on the other hand, can exist anywhere on this sphere. There's kind of like a much wider number of possibilities, different possible states these qubits can be in. They can be in 0, 1, plus or minus. I can introduce phases between the 0 and 1 components. So instead of just having a line from 0 to 1, I have this kind of nice big sphere of possible qubit states. this larger state space, as well as the different questions that I can ask my qubit, is what makes quantum information in qubits more complex than classical bits, and also gives quantum computing its power. Ooh, sorry. So we can summarize this as our two golden rules of quantum mechanics. A quantum particle can behave as if it's both here and there. That's superposition, that's a wave behavior. And measurement uncertainty. When I ask where it is, it will be found as either here or there, like a particle. So what actually happens when we measure? So let's look at what happens in Catch-22. So this is a satire novel by Joseph Heller about wartime. So at a certain point in the novel, our hero, Yosarian, is in the hospital, and he's beside the soldier in white, a soldier who is covered from head to toe in bandages and is impossible to interact with. He's, completely recovering from his wound. At one point, the nurse Kramer reads the thermometer, the only thing sticking out of the soldier in white. Nurse Kramer read the thermometer and discovered he was dead. Now that Yosarian looked back, it seemed that Nurse Kramer, rather than the talkative Texan, had murdered the soldier in white. If she had not read the thermometer and reported what she had found, the soldier in white might still be lying there alive, exactly as he'd been lying there all along, encased from head to toe in plaster and gauze. So what Yosarian is saying there basically is that by measuring it, the Nurse Kramer forced the soldier in white to either be alive or dead. Before measured, the soldier in white could have been alive, could have been dead, and no one would have known. But when the nurse made that measurement, she affected the system and, in effect, caused the soldier to die. Equivalently, in quantum mechanics, the superposition exists, but when I take the act of measuring it, I break that superposition. The act of measuring has some effect on this. This is the collapse interpretation of measurement, also known as the Born rule or the Copenhagen interpretation. We'll talk a little bit about other interpretations a bit later on. But there are other times in media where people kind of take this idea of when I observe something, I change it. And perhaps no one's done it more directly than Doctor Who, as we'll see in this next clip.
What do you mean angels? You mean those statue things?
Creatures from another world.
But they're just statues.
Only when you see them.
What does that mean?
Lonely assassins, they used to be called. No one quite knows where they came from, but they're as old as the universe, or very nearly. And they have survived this long because they have the most perfect defense system ever evolved. They are quantum locked. They don't exist when they're being observed. The moment they are seen by any other living creature, they freeze into rock. No choice, it's a fact of their biology. In the sight of any living thing, they literally turn to stone. And you can't kill a stone.
Freaky. Okay, so what are they basically saying here? We have these weeping angels, and they are chasing Carey Mulligan around. So when you're looking at the weeping angels, they cover their eyes. They are observed, they are measured, and they are frozen in space. When I look at them, they freeze. They're quantum locked. So I've effectively collapsed them to be in one specific location. But when they're unobserved, when I'm not looking at them, they're allowed to move, they're allowed to evolve, and they turn into these scary, scary things. So actually, there's a very similar effect in quantum mechanics called the watchdog effect, very closely related to something called the quantum Zeno effect. And let's kind of see how that works. So we start off with an atom that has, say, 2 electrons over here. Let's look at a helium atom. And now what I'm going to do is I'm going to shine a laser pulse on this helium atom, causing one of those electrons to start jumping or potentially jump to a higher energy level. So a photon gets absorbed by the low energy and causes an excitation to a higher energy level. Now what I want to do is I want to observe, and I want to ask that electron the question, are you in the low energy level or the high energy level? And to do that, I'm going to send in another laser pulse. So this orange laser pulse is a little bit different than the other one. It's going to cause the atom to glow if the electron got excited and do nothing if the electron did not get excited. Okay, so we're talking about atoms and stuff. Let's translate this into something that we all have experience with. So here's a piece of pizza. And what we want to do is we want to get this piece of pizza from this cold, inedible mess to this warm, barely edible mess. And to do that, we're going to put it in the microwave. Now then, the microwave is effectively like this first laser pulse. That's the one that's going to take this pizza from the cold, gross state to the warm, gross state. And this other laser pulse, this orange laser pulse, That's like pressing the button on the microwave to open it up and seeing where the pizza is at. So let's say that it takes 1 minute to heat up the piece of pizza. If I leave it there for exactly 1 minute and don't do anything, I am guaranteed to have my pizza at the end. What happens if, I press the button 30 seconds in to look at it? Classically, that means that I look at it, I put it in for another 30 seconds, and then after 30 seconds, it's done. But quantumly, whenever I look at it, it collapses to a certain state. Whenever I open it, I'm either going to see this gross cold thing or the gross warm thing, and nothing in between. So actually what's going to happen is if I don't check at all and I wait my full minute, we see this graph here, this is the number of times I checked versus the probability of the pizza being done. If I only check once at the end, I have a 100% possibility of having my pizza ready to go. If I check twice, so open it at 30 seconds, look at it, and then go for another 30 seconds, then it's something like 75% chances. As I check more and more and more, as I keep opening that microwave and looking at it, I have more and more of a chance of just collapsing it back to the ground state, back to this cold, frozen state. And effectively, in the limit where I check it like, every second, I never heat up my pizza at all. So a way to kind of phrase that really neatly is that a watched quantum pot never boils, because it has to be in one state or the other. Whenever I observe it, I kind of undo all the progress that I had made so far in getting it to that higher state. So as you can see there, I had to mix up about 3 different metaphors to get there. I had to talk about Doctor Who, I had to talk about pizza and microwaves and pots and electrons. I can't just talk about it as something that you can hold in your hand neatly with it, kind of getting all of the different properties of quantum mechanics in there. So reason number 3 why quantum is generally complicated, people, is that it's not something we can hold in our hands. It describes something that we can't see with our eyes, and that even if we see some of the effects, we see some of the results of quantum mechanics and things like the laser, we don't, see things like superposition with our naked eye. So I'm going to let Kendrick explain a little bit, but first I just want to prepare you for this amazing beat drop.
Physics could never show you the world I was in when I was 10. Back when 9 ounces had got you 10, and 9 times out of 10 don't pay attention. And when there's tension in the air, 9s come with extension.
Okay, so what does Kendrick say there? Kendrick Lamar, great track with Pusha T, says quantum physics could never show you the world that I was in. And in some sense, quantum mechanics describes everything about the universe. It underlies classical physics, but in another sense, you don't need quantum mechanics to understand the world around us. Quantum mechanics is extra. It describes something that happens underneath the surface of the universe. It has effects that boil up into large, large things, but I don't need quantum mechanics to understand how a tennis ball is thrown in the air, even though that tennis ball is made up of molecules and atoms. So this is something called the correspondence principle. And it's basically saying that quantum mechanics, in the limit of large numbers of atoms, large numbers of molecules, must correspond with classical physics. Because classical physics does a great job of describing the things around us, quantum mechanics must make those exact same predictions when we scale our systems up. If you have a theory that describes something really nice on the small scale, but when you crank up the number of atoms to a gazillion, and it doesn't match what you see in the universe around you, something's wrong with your theory. So quantum mechanics, in a sense, it wasn't born out of experimental observation in some of the same ways that we think about. It was really born on the blackboard. So it was born when Max Planck was looking at curves relating to the emission of light from hot objects. And he discovered that if he chunked up light into these little particles called photons, he could reproduce those curves much more accurately than the standard theory of radiation at that time. So this plot right here shows that it's called the ultraviolet catastrophe. And if we go back to Ant-Man and the Wasp, this is the exact plot that Lawrence Fishburne is talking about when they interrupt his class. I don't know who's designing his slides. I don't know what he's talking about there, but that is way too much information on that slide. That is, bad professoring 101. Keep your slides to one basic point. But, they, Googled quantum and put that picture in there, no problem as well. So what does this teach us though? So I don't know what he's doing with all these lines here, but he must be talking about the exact nature of light. So light is emitted in discrete bundles that we call photons, and light interferes with light like a wave. So we're going to talk for the next little bit about just what a photon is. And to kick that off, we're going to go to Plan 9 from Outer Space, another one for your movie club, absolutely. So Plan 9 from Outer Space is a movie from the 50s by Ed Wood. In this movie, the dead have been coming back to life. For whatever reason, they all look like Elvira and Dracula for no ever explained reason. And it's determined that this is actually Plan 9 by a race of aliens who are trying to stop humanity from advancing. What are they worried about? Well, I'll let them do the explaining.
The solarite is a way to explode the actual particles of sunlight. But that's impossible. Even now, your scientists are working on a way to harness the sun's rays. The rays of sunlight are minute particles. Is it so far from your imagination they cannot do as I have suggested?
Why, a particle of sunlight can't even be seen or measured.
Can you see or measure an atom? Yet you can explode one. A ray of sunlight is made up of many atoms.
So what if we do develop this solarite bomb? We'd be even a stronger nation than now.
Stronger. You see? You see? Your stupid minds. Stupid. Stupid.
Oh, I love this movie. So in this, so this alien here, he's doesn't look like an alien, but he's apparently an alien. His name is Eros. He's named after the Greek god of love because look at him. He is describing his worry that the United States of America is going to develop the solaronite bomb, which will be used to explode the particles of sunlight to create a massive explosion that's going to eventually take out the entire universe. So let's go through some of his claims step by step, and we're going to be very, very generous to him. So he says the rays of sunlight are minute particles. So if, by the word particles, he means something that you can count, something like photons, well, if we look at a 60-watt light bulb that emits something like 20 million trillion photons per second, these photons are by no means spatially small. In fact, I can have a single photon that's as large as this room that I'm in, no problem. But in terms of energy, they're definitely minute. So being generous to Eros, I'm going to give it to him. The rays of sunlight are minute. Photons, particles, whatever you want to call them. A ray of sunlight is made of many atoms. Atoms are inherently matter. Photons are inherently massless. This is from the 50s, but I mean, come on, we were beyond this by then. Not giving that one to you, Eros. Why a particle of sunlight can't even be seen or measured? We can measure a particle of sunlight using something called a photon detector. In modern days, we usually build them out of superconducting circuits where a single photon causes the little tiny wire to heat up, breaking the superconductivity. But even back then, they were doing it with something called a photomultiplier tube. So it was newer technology in the 50s, but it existed for humans. So it almost certainly existed for super advanced space aliens. So no, we could definitely measure a photon. And finally, your stupid minds, stupid. He is right on the money with that one. So let's kind of go into what he was saying there a bit. He was talking about exploding the actual particles of sunlight. So let's do a little bit of word checking for Eros real quick. Let's say that instead of explode, he meant split. And instead of particles of sunlight, he meant photons. So we always think about a photon as being a single photon. How do I cut a photon in half? It sounds like you can't do it, but Eros is actually on the money here. You can split a photon. And the way you do it is using a process called parametric down conversion. So in this process, I start with a strong laser pulse, but I can also think about this as being one high energy photon, so one blue photon. Let's say it's a photon with a wavelength that's blue, 400 nanometers or so. And I have it shine on a nonlinear crystal. So this is a crystal where when I shine laser light on it, sometimes the colors can change. If you were following the news a couple of years ago, this is the kind of work that Donna Strickland won the Nobel Prize for. So we shine our strong laser pulse into this nonlinear crystal, and with a small probability, a photon from that blue laser pulse gets absorbed by the crystal and re-emitted as two lower energy photons. So blue light has roughly twice the energy per photon as red light. So one blue photon can get absorbed and re-emitted as two red photons. This, conserves energy. In that sense, it's all fine. but it doesn't conserve photon number. We go from having 1 blue photon to 2 red photons. Because these photons are born at the same time, we actually end up with a pair of entangled photons. Importantly, there's no chain reaction or energy conversion. We're maintaining energy. So this is not a bomb. Eros has nothing to worry about, but he was a little bit ahead of the time in the sense that parametric down conversion wasn't discovered for another 10 years after this. So good on you, Eros. So, okay, the photons are both going to be created at the same point. So if the blue photon gets absorbed here, the 2 red photons must be emitted from that exact same point. We can actually see that. So this is an experiment done by people mostly at the University of Glasgow. And this is image from a camera. Well, it's image built up from 2 different cameras. So we start off with this x-axis is the x pixel, so where you find it on this line for photon 1. And this is the x pixel where you find them on this line for photon 2. And we find that, they don't always get created. There's some variation on where you find that photon. Sometimes you find them on the left, sometimes you find them on the right. But if I ever find the left photon at one position, I always find the other photon at the same position. So we see this kind of correlation. And they must conserve momentum. If one of them is kicked a little bit further this way, like has a little bit of an extra kick in that direction, the other one has to have a kick in the opposite direction to make up for it, to make sure that momentum is conserved. So we're going to see anti-correlations of momentum, and by doing a lens Fourier transform to look at the momentum distribution, we see that exact thing. So these are what we call space momentum entangled photons. Similarly, we can do the same experiment in time and energy. So the photons are created at the exact same time. Whenever that photon's absorbed, it's going to emit 2 photons at the exact same time. And we see these correlations in time. Whenever I see one photon being a little early, the other one is also a little early. This was actually data that I took during my PhD as part of Kevin Resch's lab at the IQC. And they also must conserve energy. If one is a little shifted, so it's a bit redder than average, the other one must be a little bluer than average to make up for it. And we see that as these anti-correlations in frequency or color. So they're space momentum entangled, and they're also energy time entangled. So let's back up a sec. What the heck is entanglement? So entanglement at its simplest is basically 2 quantum particles, 2 electrons, 2 photons that are not separable. So if they're separable, like in this case, I can really think about it as electron 1 and electron 2. Everything I learned about electron 1 has no bearing on anything about electron 2. If they're entangled, though, their quantum states depend on each other. Just like in this case, where I found photon 1 depended on where I found photon 2. In that case, their wave functions, their states are entangled with each other. I don't know everything about photon 1 unless I also know everything about photon 2. So in separable states, there's this clear line of separation. In entangled states, I cannot describe one without the other. Now, this has kind of given some people like a romantic notion of entanglement. So as in this figure from NASA of all places, where we think about our 2 entangled photons as being deeply in love with each other. We also have this vampire movie by Jim Jarmusch called Only Lovers Left Alive, where 2 vampires played by Tilda Swinton and Tom Hiddleston have been together for so long, they've actually developed a quantum entanglement with each other. They feel it when the other one gets hurt. It's actually a pretty good movie, even if the physics is a little wonky. And also, if you were in Vegas in 2011 and you wanted to get married, you could go to this guy's booth and they would shine entangled photons on you, and that would strengthen your bond. That would, help strengthen your marriage, because now you become quantum entangled with each other. So I have thoughts on that, but let's talk about first the most common misconception people have about quantum mechanics and how most common misconception people have about entanglement and how different kinds of fiction try to use it, to build technologies of the future. And to do that, we're going to start by talking about Mass Effect 2. So Mass Effect 2, you are sent on a mission by a very trustworthy looking gentleman, I tell you, and he's sending you all across space to find different members of a team for a mission. But because you're going through these Mass Effect relays, you're going over giant distances, you need some way to stay in touch. So they're going to find a way to stay in touch using entanglement. Let's see the science of entanglement-based communication in Mass Effect.
What's this area of the ship?
This is the FTL communications room. This allows lag-free communication even when you operate off the comm grid.
I've never heard of a quantum entanglement communicator. How does it work?
Essentially, two subatomic particles are created in an entangled state. One is installed here, and the other in the elusive man's office. When one particle occupies a given quantum state, its entangled partner will always enter the opposite state, no matter the distance between them. If we alter the state of our particle, that alters the state of the elusive man's. This allows us to send data in the form of quantum bits.
Okay.
What's this area?
So let's see what we have. What did they actually say there? So we're Shepard, and this is the elusive man, the trustworthy gentleman who is in no way going to betray us at any point in this game. So we have our two subatomic particles, and before we leave, we're going to entangle those subatomic particles so that the properties of one depend on the property of the other. Shepard is then going to fly away much further, like through this mass spectrometer, many light years away from the elusive man. And to communicate with the elusive man, what Shepard's going to do is he's going to do something. He's going to rotate his quantum bit, take the electron from the lower state to the higher state. And if it works the way that he says it does, it's going to instantaneously change the quantum bit that the elusive man has. And they can use this to communicate with each other. This does not work whatsoever. Kind of the key thing here is that while I can learn something about the other entangled bit by measuring my entangled bit, I can't change anything about the other one's entangled bit by doing anything on my side. Yeah, in order to do things like quantum teleportation and superdense coding, where we use entanglement to communicate, we need to have additional classical communication, and that only travels as fast as the speed of light. So there's a lot of details in there, but the first rule of Entanglement Club is that entanglement does not allow information to travel faster than the speed of light. So sorry to the tech squad at the elusive man's office, this doesn't work. So what can you use entanglement for? So to do that, let's look at a quick non-vocal game. So we have Alice and Bob. I've tried a long time to think of like a nice, a nice way to explain this game in a way that's kind of fun, like maybe like a casino robbery or something. I've got nothing, so we're going to keep it abstract. Alice and Bob are trying to play a game with each other. They are separated by a wall that does not allow them to communicate at all, but before they get behind the wall, they can establish any strategy that they want. They can exchange a phone book with each other and make sure they're always correlated with each other, for example. And let's make it really obvious. Let's put Alice on Uranus and Bob on Mars so that they're incredibly far away from each other. And now there are going to be two agents who are working against Alice and Bob. And they're going to ask them one of two questions, question 1 or question 2. And Alice and Bob can respond to these questions with one of two answers, yes or no. The goal of the game is that whenever they are both asked question 1, they should always agree with each other. Whenever they are asked opposite questions, so Bob gets question 1, Alice gets question 2, for example, they should always also agree with each other, either both say yes or both say no. But if they both get asked question 2, they should always disagree with each other. One says yes, the other says no. They have no idea in advance which question they're going to be asked. So, you might think about this